Hi, I want to talk about the wave diffraction effect that you get when waves interact with a narrow opening like a slit, what's also known as Fraunhofer diffraction. So what you see when you have a Fraunhofer diffraction pattern is that even if you have plane waves striking a mostly obstructed barrier at that opening, there's going to be some spreading. And with the wave, it's not just uniform spreading. You end up getting node lines heading outward at angles radiating from the very center of that opening. So if my opening happens to be coming out of the board, then the pattern is going to be spread up and down perpendicular to the direction of that opening. So if we want to figure out what this pattern looks like and where we're going to see the important features, we need to take a second to review an idea of wave propagation from pre-wave tracing called Hearns Principle. Now, Hearns was a Dutch physicist, optician, took a look at a number of areas involving physics and optics, and he was one of the early proponents that light absolutely positively had to be a wave, and his solution for wave propagation was to take a wavefront and subdivide it into tiny points. And then using a compass, you could sketch out a radius that would be the direction that a point source would be rippling a wave at a given speed. So your distance would just be the wave speed times the time you let that wave propagate. And for every point along that wavefront, you would trace out that exact same arc. So to then determine the new shape of your wave, you just draw a line connecting the tangents of all of those little wavelets, and that will show you your new wavefront. So for something like a plane wave, you have a whole bunch of parallel circles, so you just keep getting that line repeating itself again and again and again, working its way forward. Now, when that encounters a barrier, what we could do is we could imagine considering two neighboring Hearns wavelets. And I'm going to happen to choose two that are at half the size of our opening, which we also refer to as an aperture A. So I'm going to consider a destructive interference of two neighboring Hearns wavelets. So they would be spaced a distance a over 2 apart. And to get destructive interference, the difference in path from the wavelet in the center compared to the wavelet in the edge would have to be 1/2 of the wavelength of our wave. Well, because we're off at an angle, the extra distance in path by using right triangle trigonometry tells us that that extra bit of distance would be our aperture size over 2 times the sine of theta. Because our aperture size over 2 makes up the hypotenuse of a right triangle, and it's this opposite side that would be the extra travel distance from the bottom wavelet compared to the top wavelet. So, if a over 2 times the sine of theta has to equal half a wavelength, that means the sine of the angle to the first place where we get destructive interference is equal to our wavelength divided by our aperture size. Now, what happens is we get a broad region, because it's not like those are the exact 3 wavelets that we would have. These are arbitrarily drawn pieces. So we could imagine points all along that opening, all obeying that process, so we get a broad region where the whole pattern just goes dark, but then we start getting more bright regions, and then dark regions, and then bright regions, and then dark regions. So to figure out where those additional dark regions are going to be, we could think about subdividing our aperture even smaller. So instead of halves, we could imagine subdividing our aperture into quarters and looking at two neighboring wavelets. Well, my extra path length is always half the wavelength, but then here, from the trigonometry, The extra path would be my hypotenuse, a over 4, times the sine of the angle to that second dark region. So that means the sine of the angle to the second dark region is 2 times the wavelength divided by the aperture size. And we could keep going. We could divide it into sixths, eighths, tenths. Any even number of subdivisions would allow us to consider destructive interference from neighboring wavelets. So what we end up seeing for Fraunhofer diffraction is the sine of the angle from the very center of the bright region in the middle to the dark region is equal to the integer from which dark region we're looking at, first, second, third, and so on, times the wavelength of our light divided by the size of our aperture. Thanks for watching.